Now we're going to switch gears a little bit and talk about vectors. Vectors have magnitude and direction. So a lot of times, mostly up until now, we've been talking about things that have magnitude. It's also known as scalars. Now we've got magnitude and a direction for them to go in. So this would look like this. We've got x, we've got y. X is the initial. Okay, that's your starting point. And y is terminal. That's your ending point. Okay, and we've got a ray, kind of like we've been seeing when we've been talking about the unit circle. Okay, so we can call this vector xy or xy with a little arrow on top. Either way, you read that as vector xy. Okay, so let's talk about some basics. Sum of vectors is a vector. So we've got two different ways that we can sum a vector. If we can put them head to tail like this. Okay, so we've got initial to terminal right here where they connect. Then a plus b is going to be the resulting vector. Okay, so that's terminal to initial. And then we've got a parallelogram version where they both start in the same spot. Okay, let's say that's B and that's A. The resulting vector basically forms a parallelogram. It would be the same as if you tagged A onto B, or if you tagged B onto A. Okay, it would be the same result as above, and it would look like that. A plus B. Okay, so different ways of looking at the same thing, but again, you can sum vectors and it's still going to be a vector. If we have, let's say we have A looks like this, then negative A is going to be the same size, but going in the opposite direction. Let's see if I can draw it going in the opposite direction here. Like that. That's going to be negative A. So the opposite direction is going to be the direction that makes this a straight line. Okay, so this has got to be 180 degrees for it to be going in the opposite direction. We can also multiply A. So again, let's say that we have A right here. We could double A. It would be the same direction, but twice as long as A. And we could do 1/2 of A, and that would be half as long as A, but they're still going to go in the same direction as A. Of course, we need a way to be able to quantify all of this, so we can look at position vectors. So these are vectors that would be with their initial side at the origin. And it would look like this. Okay, so we could still call this vector A or B. Sometimes we use U or V for the vector names. And if it comes out here to point AB, okay, if it ends at point AB, then we say that the vector is vector AB. We can write it like that with these triangular brackets. Okay, that denotes a vector. Now we can break this vector into its two components. So this would be the vertical component. And this would be the horizontal component. And to keep things consistent with our x and y values here, the horizontal component is equal to A and the vertical component is equal to B. Or in other words, our x term and our y term, or the first value in the vector, second value in the vector. So it all kind of ties in together from what we're used to. And then of course we've got an angle here to the x-axis, and that is theta. Okay, so a lot of the things that we see here are things that we're already familiar with. If we wanted to look at the magnitude, okay, so the magnitude is denoted like this, magnitude of v, and that just means the distance here, v, just like we would have talked about the hypotenuse before. It's just talking about what number v is without the direction or the direction vector. And we can find that by doing the Pythagorean theorem. So we know that v squared is going to be equal to a squared plus b squared, looking at our horizontal and vertical components. So if we take the square root, okay, our Pythagorean theorem is going to look like that. And we put the magnitude is kind of the same as the absolute value here. We know that we're going to have to take the positive root because it's going to be a distance value. Okay, so we're looking at magnitude of v. So that's just like the Pythagorean theorem that we've seen all along. And we know that for theta, tangent of theta has got to be opposite over adjacent, so that's going to be b over a. So tangent of theta is b over a. Okay, so we're looking at it in a little bit different context here, but the values are still very similar. Whoops, that didn't work. All right, so let's look at an example. Let's say that we have the vector, let's say that we have the vector 2, 6. All right, so let's go ahead and draw that vector just so we get a little practice with it. So we've got 1, 2, 3, 4, 5, 6. Okay, that's our vector, like that. And we want to know the horizontal component, the vertical component, and theta. Okay, magnitude and theta. All right, so you can call, do we have a name for this? This is u. Okay, so we've got u this time. So we want to know the magnitude of u, and we want to know theta. All right, so we see that our a component is 2, our b component is 6, or our horizontal and vertical. So the magnitude of u comes from the Pythagorean theorem. So that's going to be 4 plus 36 is square root of 40. We can write it like that, or we can write it as 2 square root of 10. I'm not too picky either way. Okay, so if we pull the 4 outside, it's going to become square root of 4 is 2. Alright, so there's our magnitude of u. And to find theta, we know that tangent of theta is opposite over adjacent. So we've got tangent of theta is equal to 3. So we can do tangent inverse on both sides to cancel it out over here. So we're going to have tangent inverse of 3, and we're going to need our calculator for that one. Let me look it up real quick. Okay, tangent inverse of 3 should be 71.6. Okay, so there's our magnitude. That means this distance right here is 2 square root of 10. We can change that to a decimal if you want to just kind of make sure that that makes sense. 2 square root of 10 is about the same as 6.3 over here, 6.3. So that does make sense. That seems reasonable for this triangle. And our theta, our angle right here, is 71.6. And again, that seems pretty reasonable.